It's the metal synonymous with strength. The backbone of buildings that scrape the sky. We mine it. We forge it. We even eat it. It makes weapons that alter the course of war. But it's also the key to coloring our world. And it's alive with a force of nature as perplexing as it is powerful. Now, the untold story of iron on Modern Marvels. Iron, the most abundant element on Earth, is the stuff that civilization is made from. It's everywhere. The indispensable heart of our buildings. Cars, ships, tools, and weapons. But it's also the foundation at the core of our Earth and courses in our very blood.
Iron's incredibly important to our survival. It's part of our entire being. Without iron, life as we know it wouldn't be possible.
Iron is invaluable not just because of its unique strength, but because extreme heat can make it surprisingly pliable.
Iron is one of the few things on Earth that can go from an ore like this through fire and forging and become a tool like this that'll last for generations.
Iron's muscle comes from its atom's superior ability to share some of its 26 electrons with other iron atoms, forming a vice-like bond. There's no limit to the size of the resulting lattice structure.
So that's the secret of its strength, because the sharing of electrons between two iron atoms is essentially the glue that holds a piece of iron metal together.
As strong as iron is, it's easily reshaped. Since temperatures over 2,800 degrees Fahrenheit enable us to break the bonds between its electrons and melt it.
You can actually rip apart that glue. The iron atoms are all floating around in a liquid soup of iron atoms. This is very useful for us for a number of reasons. If you want to, you can pour it into a mold and essentially cast that iron into whatever shape that you want.
Iron in the form of steel is the most recycled material in the world. Nearly 70 million tons find new life every year in the United States alone.
Iron and steel are endlessly recyclable, such that the steel used in a Model T could have been used in an ice box, could have been used in a building structure, then used in the vehicle you're driving today. The same iron.
Another useful aspect of iron is that it lies within easy reach, right beneath our feet. The Earth's crust is comprised of about 5% iron ore, and miners extract 1 billion tons of it every year. This enormous open-pit mine in Minnesota taps one of the largest deposits of iron ore in the United States. The ArcelorMittal Minorca mine processes more than 10 million tons of iron ore a year.
This pit that we're standing in right now is about a mile wide by about 3,000 feet in length. We mine several layers of ore here. We're right now about 400 feet down to the bottom of the pit. Open pit mining is a methodology of mining where you excavate and take off the stripping materials. The waste materials are on top of the ore, expose the ore, and essentially in the process make a giant hole in the ground. The demand for iron is so great that we run this operation 24 hours a day, 7 days a week, 365 days a year.
Where did all this iron come from? Billions of years ago, long after the Big Bang, stars created heavy elements within them until the stars became supernovas. One in particular helped create the Earth.
When that dying star exploded, it blasted iron and the other elements all over its area of the galaxy. When the Earth first formed, it was a grand mix of elements, the remnants of this supernova. And then, as that stuff segregated out into various pockets, the iron, which is very dense, sunk by and large to the core.
In fact, 98% of the Earth's core is iron. But enormous quantities of iron stayed on the Earth's crust, sometimes in the form of deposits, like a mountain range full of pure iron that stood in what is now Minnesota. The first rains that fell on Earth were highly acidic and dissolved the iron mountains, creating an iron-rich ocean. A few 100 million years later, the dissolved iron solidified and settled to the bottom, leaving the deposits we mine today.
Here in Minnesota, we believe we have enough iron ore to last mining activity for another 100 years with the iron that's currently making ore today.
The ore extracted here is an iron oxide called magnetite, which is 22% iron. Until the late 1940s, America's iron miners dug a richer ore called hematite that's 65% iron. But the enormous demand for iron during World War I and World War II severely depleted the nation's hematite resources.
This is hematite, the rock that was initially mined in Minnesota. It's red in color because of the oxidized iron. It looks much like the rust you'd find on steel or iron if it's left to weather. This is magnetite. This is what we're mining today. It's black in color and has a lower iron content than hematite.
10 seconds to main blast.
Getting to the magnetite ore starts with a bang.
3, 2, 1.
Then, loaders transfer the blasted ore to production trucks. After crushers and grinders reduce the iron ore to a powder, mixers combine it with water to form a slurry. The slurry then passes through magnetic separators.
The magnetic separators are large drums that are 10 feet in length, 4 feet in diameter, and contain stationary magnets. As the drums rotate, they pick up the magnetic iron particles that are in the ore and separate them from the non-magnetic particles.
Machines mix the iron slurry with clay, which is then molded and baked at 2,400 degrees Fahrenheit into convenient, easy-to-transport, marble-sized pellets. 98% of this iron will be used to make steel. Structures from the Golden Gate Bridge to stadiums and skyscrapers. They're all made of iron at their core. To make steel, iron must be 100% pure. Impurities, which include oxygen, must be stripped away. Melting the iron is the key to this trick, in the intense heat produced inside a blast furnace. The furnace burns coke, a purified form of coal.
It's called a blast furnace because the amount of air that is shoved into the system. It takes incredible amounts of air to get the temperatures necessary to make steel.
In the blast furnace, carbon from the coke is infused into the iron to make steel. Too much carbon will make it brittle. So just a small amount, no more than 2%, is all it takes.
This is a snapshot of what iron looks like on an atomic level. When you make steel, you've actually taken the crystal structure of the iron and you've crammed a carbon atom into one of the holes in the crystal structure. What this does is it makes it harder for you to slide the iron atoms around with respect to each other because you've got this guy crammed in there. The presence of this carbon atom, a bad fit as it is between these iron atoms, is what gives steel its great strength.
Adding other elements or alloys to this fusion of iron and carbon produces a variety of steels that have different properties. For decades, the iron atom's flexibility has helped the steel that surrounds us to vary greatly in its strength and pliability. And now, with modern computer technology, experts are able to mix more precise amounts of alloys to iron to produce a new enhanced generation of steels.
We call them the new advanced high-strength steels. They are 5 to 6 times stronger than the steels we've used in the past, making vehicles lighter, safer, and more fuel efficient.
Since 2000, all major auto manufacturers have been incorporating the new advanced steels into their car bodies.
The value of these steels in a crash is their ability to absorb energy. So rather than the passenger absorbing the energy, your vehicle structure takes the energy and keeps the passenger safe.
The new steels have proven their strength and durability in drop tests, in which a 400-pound weight drops from 20 feet to simulate a 35-mile-an-hour crash.
This is the result of the drop test. Here's our sample. With the old steel, it crushes 6 inches. With the new steel, it crushes 3 inches because of its increased strength and energy absorption capability.
If you think adding strength to this new steel also means adding weight, think again.
Here's an automotive component made with the old technology. It weighs 40 pounds. Accomplishing the same structure with the new technology is considerably lighter, you can see, and it weighs 32% less in weight.
Since the new steels are lighter and stronger, less is needed to meet crash safety standards. Today, the typical car body contains 10 to 15% of the new generation of steels in its construction. By 2020, experts predict this will increase to 40 to 50%.
When the new steels are fully implemented on the car body, they'll be applied to the rail and to the bumper for front impact, into the safety cage structure for side impact and for roof strength, as well as to the door beams for side impact. And for rear impact, they're applied to the rear bumper and to the rails.
China is the #1 producer of iron ore in the world, mining 10 times as much as the United States, which is 7th. Iron will return on Modern Marvels. We now return to iron on Modern Marvels. Iron in the form of steel lies at the heart of every nation's arsenal. And that should come as no surprise, because iron and the development of weaponry have gone hand in hand since antiquity.
Empires that were able to produce the best iron weapons were the deadliest armies and those that were able to conquer their foes.
Iron began revolutionizing warfare over 3,000 years ago.
First crude weapons that men used were made out of stones. These were replaced by bronze, but when iron came in, now you had a weapon that could be sharpened, would keep its edge, and even last for generations.
The first iron weapons were made with iron extracted from meteorites.
It was called swords in the heavens, because you could take meteorite iron, which is almost pure iron, and beat out weapons such as knives or swords.
Whether separating iron from meteorites in that era, or smelting it from iron ore, making iron pliable required extreme heat. How did the ancients manage it? Workers built a mound with a hole 1 to 2 feet in diameter at the center. They lined the hole with fire-resistant clay or stone. Next, they placed a layer of charcoal on top of the clay, which they ignited. On top of that, they set the iron ore. Earlier, bronze and copper had been smelted this same way. But smelting iron required an infusion of air to make the charcoal burn at iron's higher melting temperature.
With the air coming in, that kept the heat at a high enough level. By heating this up, the oxygen gets stripped away from the oxide and carried away with the waste gases from the fire. And that leaves you with the pure iron.
After workers smelted the iron, they formed it into a bar called wrought iron. Ancient weapons makers then literally beat the wrought iron into shape in a process called forging.
At forging temperature, or about 1900 degrees, the iron is very pliable. So I can take the hammer and drive it into whatever shape I need.
Ancient blacksmiths forged spears, knives, and swords, which were stronger and more durable than their bronze and copper predecessors.
This piece of iron now, after we've done all this work on it, will last for many generations.
Iron's strength and durability made it ideal, not only for weaponry, but also for defensive purposes. For centuries, wrought iron was the go-to metal for making helmets, shields, and suits of armor. Iron weapons took a quantum leap forward, starting in 16th century Western Europe.
The first muskets that were made, we believe, were made like small hand cannons, where a sheet of wrought iron was rolled and the edges welded together, and it was formed on the end of a pole or a pike.
The wrought iron musket barrel achieved devastating effects on the battlefield.
In the era of forged iron barrel muskets, plate armor didn't have a chance.
Beyond the wrought iron used to make muskets was cast iron. This was essentially iron melted down to a liquid, which was poured into a mold or cast, and then cooled.
This is an example of cast iron. This is all one piece. The advantage of making pieces of cast iron this way is you can make multiple pieces that are just alike and in a very short period of time.
But cast iron has one major problem. It's brittle. We now return to iron on Modern Marvels. In 1856, British engineer Henry Bessemer found a way to make a stronger form of iron by combining it with carbon in a blast furnace to make steel.
Now with steel, you could cut it, you could mill it, you could shape it into not only a tube, but also a breech-loading barrel. With the addition of metallic cartridges, you could make a very successful not only breech-loading weapon, but a repeating weapon as well.
In 1862, the Union and the Confederacy began armoring their warships during the American Civil War.
The ironclad ships, they were made from sheets of wrought iron. These sheets were applied either to a wooden hull ship, such as the Merrimack, or the entire ship was made of sheets of wrought iron that were riveted together to form the hull and a turret on top of the deck, as in the case of the Monitor.
In their one and only battle, both ships received dozens of direct hits, but remained afloat. In the end, the battle was a draw. Iron proved to be the real winner, changing naval warfare forever. By the 20th century, iron-rich hematite supplied America's vast steel industry. In 1915, steel supported a new mechanized war.
The tanks of World War I were known as land ships. Just like the ironclads of the Civil War revolutionized naval warfare, these land ships of all steel revolutionized land warfare.
The iron battlefield helmet, which first appeared centuries ago, was reintroduced during World War I, this time in the form of steel.
This is an original World War I helmet as worn by the British and United States troops. It's made out of thin sheet steel. It's been stamped the same way you would see a car body. The idea here is not to protect from bullets. It is to protect from iron shell fragments that have been tossed down from exploding shells from above. You see, most soldiers spent 4 years fighting in trenches dug in the ground.
World War II consumed nearly the last of the hematite iron. More than 65 million tons of ore was produced in 1944 alone, allowing American steel to rule the battlefield, the oceans, and even the skies.
Began to use all-metal airplanes instead of those made of wood with a canvas fabric coating. Steel began to replace all other organic materials for weapons.
Today, iron is still the most important metal in every nation's military, as the principal component in all forms of steel. But one configuration of iron as steel has proven to be warfare's most dangerous weapon: the barrel of a gun. The M16 rifle has been the U.S. Army's standard issue weapon since the Vietnam era. Its plastic, aluminum, and steel construction is designed to be lightweight and portable in combat conditions. But to achieve pinpoint accuracy, gunsmiths at Fort Benning, Georgia, use a heavier steel.
Getting rid of the plastic, aluminum when you can, you end up with a much better product. And adding iron to the rifle makes it a much better rifle, a much more accurate and much more precise.
They beef up the M16 rifle for the elite Army marksmanship unit.
Take a standard issue M16 and we basically rebuild it starting at one end to the other.
The M16 barrel is reinforced with high-grade chrome moly steel. It's made of over 85% iron and a critical 1% chromium and 0.2% molybdenum. With each shot, the barrel must stand up to the force of a bullet speeding 3,000 feet per second, with a pressure of 65,000 pounds per square inch. The Army fashions the modified M16 barrel from a piece of raw stock called a blank.
What we're starting with is a 9-pound rifled blank to make an M16 barrel. We have to machine the exterior profile. It's going to end up being around 4 pounds, so we'll take about half that weight off. You've got areas that need to be within 1/10,000th of an inch, which equates to 1/40th of the thickness of a sheet of notebook paper. And those tolerances have to be extremely tight for accuracy and reliability.
This is the standard M16 rifle. This is our modified Marksman M16 rifle, as you can tell by its custom-made barrel. This target was shot with a standard M16 rifle, and it's about a 7-inch diameter group. This target was shot with a modified match M16, and it's about a 1.5-inch group.
The average weight of a medieval suit of wrought iron armor was about 40 to 60 pounds. Iron will return on Modern Marvels. We now return to iron on Modern Marvels. One of iron's most curious properties provides the motion that powers the machines of our world. It's magnetic.
Magnets are so important to the way the world works. The forces between magnets, the attractions and repulsions, can make things move.
This is a supermagnet, made of iron combined with a couple of other elements: boron and neodymium. It is 100 times stronger than the magnet on your refrigerator.
Supermagnets can be very dangerous. They exert such enormous forces on one another that if your hand is in the way when they leap, you're in trouble. I've put one supermagnet inside this wine glass, and I'm going to bring the other supermagnet up toward it.
This attractive wonder is a so-called permanent magnet, an iron-bearing metal that retains its magnetism after the removal of the magnetic force. That force can either be another permanent magnet or a jolt of electricity. Another form of magnet, an electromagnet, is magnetic only when energized by electric current. Combine electricity with any piece of iron, and you've got an electromagnet.
This is a piece of ordinary iron. It's not magnetic. It won't pick up the other bolts. To make it magnetic, I'm going to wrap this wire around this bar. Now, when I run electric current through this coil of wire, it will turn into a magnet, an electromagnet. And now, it picks up the iron. But if I cut the power, magnetism goes away.
This property is the key to movement in electric motors that power our industry. An electromagnet called the armature revolves between the north and south poles of a stationary permanent magnet called the stator. The armature rotates until its north pole is opposite the south pole of the stator. The direction of the armature's current is then reversed. The two south poles repel each other, pushing the armature forward. The current reverses every half turn, keeping the armature in motion. Iron is not only an integral part of the machinery powering our world, but also a mineral nutrient within each of us, crucial to our biology.
The same iron that everybody sees around the world is the same iron within us as small microscopic particles. And without this iron, we will cease to live.
We help maintain our body's vital supply of iron by ingesting iron contained in meat and from vegetables. Another source is certain brands of fortified breakfast cereals, which contain iron baked right into the flakes.
There actually is a scientific way of determining the amount of iron present in a fortified cereal.
All it takes is grinding up the flakes into a mash and using a magnetic stirring bar. The iron in the cereal is attracted to the magnetic bar. Then, a quick rinse.
There's about 8 milligrams of iron present in a bowl. When you start the day with a fortified breakfast cereal, you're actually eating pure iron filings.
Whatever its source, iron's critical mission is transporting oxygen through our bodies. Normally, combining iron and oxygen produces iron oxide, sometimes known as rust, which, no surprise, could do our bodies great damage. But iron, which exists in our red blood cells, latches on to oxygen molecules. So why doesn't it turn to rust? The body's intriguing solution is to place the iron in a cage-like molecule called heme.
Heme is a beautiful cage that is made inside our body. It captures and encloses the iron in the center and prevents it from turning to rust when it binds to oxygen.
The iron and oxygen inside the heme attaches to a protein called globin. The new molecule, hemoglobin, travels in the blood, delivering oxygen throughout the body. But the genes that control this iron-dependent transportation are elusive. Discovering them is critical, because more than 2 billion people, a third of the world's population, are anemic, lacking sufficient supplies of iron and heme. Anemia can weaken the body's immune system and trigger life-threatening infections and diseases. This microscopic transparent worm may be the key to unlocking the mystery. 70% of its genes are identical to ours, and like us, it needs iron and heme to survive.
So what we did was we took a small amount of iron and heme and put it on this petri dish. So we can directly look at now what happens in a transparent animal as they're actively feeding on this iron and heme.
Dr. Hamza conducted experiments in 2007 that revealed some of the worms digested iron less successfully than others. He went on to identify the missing or mutated genes of those worms, marking a major breakthrough.
We were ecstatic because this will now provide us with a small clue as to how we transport iron and heme. This will provide us with the missing link between iron deficiency and anemia.
Iron magnets can be found in your cell phone, stereo speakers, vacuum cleaner, refrigerator, washing machine, and car. Iron will return on Modern Marvels. We now return to iron on Modern Marvels. Iron's hallmark is its strength. But this indispensable metal girding modern civilization has one key weakness. When exposed to air or water, iron turns to rust.
We don't like rust because it weakens our structures, our buildings, our bridges, and it's quite a serious problem. It's a multi-million-dollar industry trying to control it, trying to stop it from happening.
Rust is the result of a chemical reaction in which the 26 electrons within the iron atom again come into play. 2 of those electrons orbit the nucleus farther away than the rest.
These electrons are sort of like black sheep. It would make the iron molecule a lot more stable if these electrons would go away, basically. Oxygen, on the other hand, needs a couple of electrons, so it's very eager to take them. So what happens is they come together, they combine, and they form a new compound called iron oxide.
And that's iron's archenemy, rust. Since the added oxygen makes the iron oxide molecule larger than the parent iron molecule, the rust displaces the iron and is clearly visible on the surface.
The main things that we can do to protect surfaces from rusting are to coat them and stop the ability of oxygen and water to get to the surface in the first place.
However, there are some who don't mind a little rust. In fact, they want all they can get.
We love it. Rust is us. Everything we do involves rust. Our world is rust.
At Rockwood Pigments in Los Angeles, experts are taking advantage of iron oxide's beneficial ability to color our world. Nature crafts iron oxide, the same stuff dug up by iron miners, in a variety of earth tones. But Rockwood makes pigments in factories in the U.S. and around the world, from iron oxide derived from industry's iron leftovers.
We take forms of iron, mostly in scrap steel, and oxidize it in sulfuric acid, and then control that reaction to make different forms of iron oxide.
1 ton of scrap metal makes 1.5 tons of pigment because of the extra oxygen molecule. 50 million pounds of iron oxide arrive at the Rockwood Pigments Los Angeles plant every year in 3 basic colors: red, yellow, and black.
These are 2 bulk sacks of iron oxide. Each one weighs 1 ton. Together, it's as much as an SUV.
Various combinations of the 3 pigments enter a blender where up to 5 tons can mix at one time.
Our main concern here is to make sure that all the red, yellow, and black, or the combination of pigments, are mixed together so that we don't get streaks in the finished product.
In Rockwood's quality control lab, workers mix the powdered pigment with a liquid binder of clay and water. This sample batch is then compared to the standard color to ensure consistency.
This is the standard, which we know is good. This is the batch which we're making. Obviously, we'll be adding some yellow shade red and sending it back to production for rework. This is our standard again and our batch. Everything looks good after adjustment, ready to ship to the customer.
The idea of using iron oxide as pigment is as old as history itself. In fact, it was used to record history as far back as 17,000 years ago. Today, iron oxide paintings still endure in France's renowned Lascaux cave. The basic concept endured for centuries as well. and late medieval and Renaissance artists used iron oxide pigments for their rich, warm red and orange colors.
Everyone from Michelangelo to Da Vinci to Rembrandt and beyond have used iron oxide pigments.
Today, Rockwood Pigments continues iron oxide's colorful legacy. But most of its pigments end up not on a canvas, but in concrete.
Most people wouldn't know that concrete is colored. For instance, the floors you walk on, the concrete block that are structures, the pavers that are in our homes, roof tile on the top of homes, all of these are concrete applications that have been colored with iron oxide. In a year, Rockwood Pigments makes enough iron oxide that would color concrete that could cover the state of Texas.
But your closest encounter with one of Rockwood's iron oxide pigments comes every time you open your wallet.
We make hundreds of tons of black pigment that gets used in the color for the U.S. currency. This black pigment is so concentrated it makes millions and millions of bills.
Iron oxide black is used in the ink that goes on the dollar bill because it doesn't fade, it's light, fast, durable, and it will last a long time.
The ancient Egyptians, Greeks, and Romans used natural iron oxide pigment for cosmetics. And it's still used in cosmetics today. Iron will return on Modern Marvels.
Duncan just protected his family with a $500,000 life insurance policy. How much do you think it cost him? $100 a month? $75? $50? Actually, Duncan got his $500,000 policy for under $27 a month, less than $1 a day. His secret? SelectQuote. In just minutes, a SelectQuote agent will comparison shop nearly a dozen highly rated life insurance companies and give you a choice of your 5 best rates. Duncan's wife, Cassie, got a $350,000 policy for under $13 a month. Give your family the security it needs at a price you can afford.
Since 1985, SelectQuote has saved over 1 million customers hundreds of thousands of dollars. Call SelectQuote now, 1-800-649-9058. Or visit SelectQuote.com. Discover what over 1 million families now know. We shop, you save. Call now.
We now return to iron on Modern Marvels. As NASA's Mars lander, the Phoenix began searching for signs of water on the red planet in May 2008. A different treasure was right at its feet.
Mars is covered with rust. Mars is known as the red planet because of the iron oxides present in the Martian soil.
There's probably billions of tons of iron on Mars that would satisfy civilization for hundreds of years, if not thousands of years.
While the Earth's crust is less than 5% iron, the crust of Mars contains 14%. This vast resource beckons the futurists, including researchers affiliated with the Space Commerce Company, 4 Frontiers. They're studying ways to mine beyond Earth.
4 Frontiers got its name from Earth, asteroids, Moon, and Mars. And the 4 of these makes our 4 Frontiers. My role as a geologist is to find enough minerals for us to have a society to live on.
Some estimate that within the next 50 years, human colonies may be established on Mars, where mining would be a breeze compared to the process on Earth.
On Earth, for us to get to the iron, we have to create these gigantic open pits that you see in front of us, where they go down hundreds of feet just to get to the iron, and they cover hundreds of square miles in the end. Whereas on Mars, all of the iron ore is sitting right on top of the surface, and although it covers hundreds of square miles, we don't have to dig down very deep, maybe about 18 inches, so that's a lot different than what you see in front of us here.
The Martian surface may prove to be even more user-friendly than imagined. The pictures sent back from the Mars rover missions suggest that natural processes have already accomplished a key part of the mining.
When the probe landed on the Mars surface and started roaming around, they started noticing all these little round pellets, and they were wondering, what in the world is that? And they discovered that they was actually iron minerals.
Scientists believe those pellets contain amounts of iron similar to the man-made pellets that need to be mined, crushed, and baked here on Earth.
What's really good about the iron ore deposits on Mars is they're already in pellets. We don't have to go and manufacture these and mine them and make little pellets. It's already there for mining, and we can go ahead and put them in a blast furnace.
Martian mining offers one further advantage over Earth.
Gravity on Mars is about 38% of what it is on Earth, so everything is a lot lighter. We don't need the big heavy machinery because everything is on the surface. All we have to do is just scoop up the iron minerals and transport the iron minerals to our community where we'll convert it into iron metal.
The iron mined would be refined on Mars itself to help build the infrastructure of extraterrestrial colonies on Mars and beyond.
Okay, now we're on Mars. We have to have a place to live. We have to have instruments. We have to have machines, and therefore we have to have iron. And it's way too expensive and way too heavy to bring that iron from Earth to Mars. So we want to find it on Mars and use it there. And once we start manufacturing the products, then we can take it into the other heavenly bodies. This is like a way station for our expansion of our people into space.
As rich as the treasure of iron on Mars is, the true mother lode is on asteroids. Some scientists believe they're comprised of up to 98% iron.
There's about 4 or 5 asteroids that we think are principally iron deposits. And these asteroids are so big that they actually have more iron than we've ever produced on planet Earth.
Only time will tell if dreams of mining this essential metal in the heavens will come true. But even if our only source remains here on Earth, our need for iron promises to endure as long as we do.
We'll always have iron. Iron will always be a central part of our lives. It's part of our structures. It's part of our motion. It's part of us. We'll never be without iron.
Nie, to już nie fajnie tak było, machanie przy niczym. Cześć, dobra.